when a system is booted, right? When a system starts how all this trustworthiness walking takes place. I'm going to simplify things a little bit. You can take a look at the actual details, the nitty-gritty in the books. We have two very good books, one by IBM guys and one by Intel guys. The Intel book is quite old, and IBM, the practical guide, just a computing guide, new. It has codes and it's very detailed. We'll get to that in a little while, but we can discuss the overall flow here. What happens is when the systems start, in normal cases, you go to the BIOS, right? There are some, don't know the details here, but you go to the BIOS. In a TTM equipped system, what happens is the control is first passed on to the TTM. Right? What the TTM does is it measures the BIOS. How does it measure the BIOS? It takes a hash of the BIOS, the code that is the BIOS, right? It takes a hash. The hash is SHA-1, secure hash algorithm, and that is a 160-bit hash. Whatever code you give to it, it reduces it to 160 bits, right? And this is secure and it's irreversible, and there are certain properties that are used here which you can take a look on your own. The point is that once you have a SHA-1, you cannot go back from this point to this point. You cannot retrieve the original from the hash. That is why it's called the secure hashing algorithm. In MD5, there are ways of breaking it. SHA-1 has also been broken, but that is in the very far future. 5-10 years later, it will be replicated. But right now, it's secure. It's all criteria. So what happens is the TTM takes the hash SHA-1 of the BIOS and stores it in a location. This location is within the TTM. It has a special name. It's called a platform. Configuration register or PCR. There are many PCRs in a TTM. They're normally in multiples of 8. That's actually the specification. They have to be in multiples of 8. You either have 8 PCRs or 16 PCRs or 24 or 4. Right? That is the specification. These are shielded memory locations. Right? They tamper resistant. You cannot take a, for example, electric circuitry and or magnets and all that and manipulate these resistors. You cannot do that. They're shielded. Right? So basically, they are resistant to software attacks. There are only a very limited number of ways of changing these values, the values in these PCRs, right? Very limited number of guidelines. Secondly, they are resistant to several hardware attacks, several easy and cheap hardware attacks. If you take a hammer and you break the TTM, the PCR will be destroyed, right? The goal is to resist normal situations in which, for example, a person comes in and within 5 seconds destroys your system, right? That will be protected by the TTM. Or the figure that they used was $20 to $25 worth of equipment. That is the target. The TTM will resist that equipment. But if you go, for example, a high-tech equipment that is $500 or $600, then the TTM probably will not be able to take care of that, right? But it is resistant to several hardware attacks. Right? Again, which hardware attacks you can take a look at in the book. So, we were here. The TTM started, it took the hash of the BIOS and saved that hash in one of the PCRs. In normal system, everyday the system that we have 24 PCRs. PCR 0 to 7 are for this whole procedure that we are making. Right now. PCR 8 to whatever are from other purposes. I will use PCR 10 in something like that. So, the hash is stored in one of these PCRs, 0 to 7. Okay. The BIOS is then passed to the control. So this is 1, this is 2. Now what does the BIOS do? It has to load several of, right? Whatever it loads, these are several modules which frankly I am not sure what they are, but these are the different modules which are involved in the loading of the bootloader and the different hardware and stuff. So it measures this and saves this hash here. It does not replace it. We see how it actually takes place. But then passes control to here. So this is 3. And this happens until you get to the bootloader. Bootloader is measured and control is passed on to the bootloader. Right? Up till here, everything is included in the specifications of the GPM. Right? This is the procedure that the manufacturer has to implement. For example, if you buy a system from Dell and they install TTM in there, they have to write a customized version of BIOS which can take the hash of whatever it loads, right? And then pass control on to it. Similarly, if you not this step, this is not the concern of the manufacturer. The bootloader is not the concern of the manufacturer because it is a customizable software. A user can customize their own bootloader on a PC. On mobile, the scenario is a little different, but on PC, the bootloader can be easily modified. Right? So the bootloader is not the concern of the manufacturer, but everything on the top is the concern of the manufacturer. They have to build customized hardware as well as customized software for it. So once the control is passed on to the bootloader is measured. But the bootloader does not measure anything. The bootloader that we take the example of is GRUB. The Grand Unified Bootloader. That's the normal everyday bootloader in Linux. So the bootloader does not do anything. The specs stop here. The trusted computing specs stop here. As you can see, the problem is even if you have measurements of all of these, the system is composed of several other things. Most of all the operating system. There is no mention of the operating system here. No one is measuring the operating system. No one is measuring the bootloader. No one is they are measuring the bootloader, but the bootloader is not measuring anything. So whatever operating system is being loaded, that is not included in this trust measurement. Right? What we need to do is somehow enable this bootloader to measure the operating system that it's loading, right? And that is where the story of IMA starts. What IMA does is take this exact same procedure, and extends it to within the operating system. We are here. We have a bootloader. Now the bootloader measures the operating system, the kernel of the operating system, puts this hash in CCR10. Let's not say put, let's say record this hash in CCR10. Right? Now the kernel is modified to whatever kernel node, for example, it nodes init, the first initialization script. It first measures init and then passes control on it. The same thing that was going on here, right? It measures init, stores the hash here, and then passes control on it. Now the thing is that in the kernel, everything does not have control as here. For example, here the BIOS had all the control. The BIOS was supposed to load whatever was coming in, and that thing was supposed to load whatever was coming in. until we got to the bootloader, and the bootloader was supposed to load the kernel.